Hello everyone, today we'll talk about the solution to the problem find the minimum diameter after merging two trees. Of course, since this is asking us to return a diameter of some tree, with the definition here, we have to know how to find the diameter of a tree. So if you don't know it, it's a prerequisite, but I'm going to go over it quickly. The algorithm that I prefer to use, and I think that it's preferable because it's very easy to remember it, even if you are not able to prove its correctness immediately, though it's not that difficult to prove it. The algorithm is very simple, and given that you have a tree, because diameter of a tree and diameter of a graph are two different problems, you can take any node on your tree, find the furthest node from it, and then find the furthest node from that furthest node, and this second path that you find is the diameter of the tree. It's one of the paths that are the longest possible simple path in the tree. So essentially it's the longest from the longest, very easy to remember. To prove it, you can try to think about, because of course you know that in a tree any two nodes have exactly one shortest path connecting them, and when you have three nodes then their paths will meet at some point, and you can either do some casework or notice some things when you want to prove it. Either way, we want to know how to find the diameter of a tree, so this is the algorithm. And now how to solve this problem? Well, this is just the final piece of the puzzle. The minimum diameter after merging two trees is either the diameter of the first tree or the diameter of the second tree, because still they are not getting smaller, so their diameter cannot decrease. Or after the connection, the diameter uses the edge that we use to connect. Which means that we connect two vertices, one from one tree, one from the other. And that means that the diameter is essentially the furthest vertex from one of the vertices that we connect, and then the furthest vertex from the other node that we connected. Right? So this is our edge, the furthest from one end and the furthest from the other end. And part of the meaning of the diameter, part of the usefulness of a diameter, is that a node that lies in the middle of the diameter, so that's either equally distant from both of its ends, or one path can be longer by one, because the diameter can be either odd or even, then that node there is no further vertex from that node than those two vertices that lie on the diameter. It's very easy to see why, because if we have the node on the middle of a diameter, then if there is some node that's further from it than both the ends of our diameter, then we can take one end of the diameter and that other node that's even further, and we get an even further path. So this is a contradiction because that would be longer than the diameter. So what do we want to connect? We want to connect the middle node of one diameter to a middle node of the other diameter, and as we said, the final length of that diameter would be 1 because of our edge, plus half the diameter of the first tree, plus half the diameter of the second tree, and we have to round up in every case, because if we cannot split the diameter in the middle, the longest diameter that we generate will take the longer of the two paths. So, find the diameter of one tree and of the other tree, and get the maximum of those two and of the combined diameter. And the algorithm that I mentioned, this will have a function BFS. First of all, we convert our tree into a graph, because we'll be running a BFS on that graph. And now we run BFS from an arbitrary node, let's say 0. We take the furthest node, we run BFS from the furthest node, and we take the length of the path that we've found. Note that we do not even have to here find the middle nodes. We don't have to tell which nodes we connect, we only have to report the diameter. And the BFS, very standard. We have a queue, which is dec in Python, set of seen vertices, the number of steps that we've taken, and we go through all the vertices in a standard BFS fashion, counting the layer that we're on. At the end, we return v and step. V is and this is also something that we can do in Python. Since v here, we have it assigned, and so v will be the last value which we have assigned here, which is the last value that was ever on the queue. So we can just return that last value, because we care about any of the vertices that are on the last layer, which might as well just be the last vertex in our queue. And this is the whole solution.